Okay, our next chapter in chapter 5 is vector space. Okay, in chapter 4 we have studied vectors in 2 dimensions and 3 dimensions. But now in this chapter we will extend the concept to more than 3 dimensions. For example, vectors in 4, 5, 6 and so on dimensions. Okay, so we will extend the dimensions of vectors in this chapter. Okay, what is Euclidean and space? So for space, more than 3 dimensions, we call it Euclidean and space, where we will name the space according to the dimensions that we are referring at. Okay, so R is set of real numbers. If n at least one an ordered sequence given by A1, A2 until AN. This is the components in the vectors in space N. Okay, so we call this an ordered N tuple. We call it tuple. Okay, for more than 3 components, we call it tuple. Okay, so R subscript N is a notation for n space. Okay, a tuples, n tuples in the Euclidean n space. Okay, we write in a standard form like this, where R subscript n equals set of a component or n tuples written by A1. A1 means that in a direction I, J, K and so on until n. Okay, where AI is an element of real numbers in n space. Okay. Okay, so all the operations in the 2 and 3 dimensions will be the same in n space dimension. Okay, for example, two vector, equality of two vectors. Let's say we have two vector u and v given this component in the n space. So we just compare the respective component and get the value. Okay, for example, u1 equal v1, u2 equal v2 until un equal vn. So that is equality of vectors. Okay, next operations in addition and scalar multiplication. This one also same as in 2 and 3 dimensions, where if we were to add the two vectors, so we add up the values in the same component or same direction. Okay, like this one. And if the vector is multiplied by scalar k, we just multiply the scalar to each component given in the space n. Okay, so this is for addition and scalar multiplication. Okay, for inner product, remember in inner product is the dot product. Okay, inner product is the dot product. We call it inner product in the space n. Okay, inner product between u and v in space n. Okay, inner product of vectors. Okay, let's have a look at this example of inner product of vectors in space 4. Okay, for example, u given by this vector and v given by this vector in a space 4th dimension. We have a 4th dimension where n equal to 4. So now for inner product or dot product, u dot v equal, so we just multiply value from the same component. Okay, minus 1 times 5 plus 3 times minus 4 plus 5 times 7 plus 7 times 0. Okay, so this is the inner product. Okay, for norm and distance, in the Euclidean of n space, okay, for norm or length, distance. Okay, the symbol for distance. So the symbol, okay, for norm and distance in Euclidean of n space, so the length or the distance of a vector is given by root of each component square. Okay, so the summation of each component square. So this is the norm. Okay, for the distance, we take the difference between the two vectors. Okay, the difference between the two vectors between u and v. So the distance is root of, take the component of u, each component of u minus component of v. Okay, example. Okay, let's say u given by 1, 3, minus 2 and 7, and v is 0, 7, 2 and 2. So the norm of u is given by, so take the root of each component square. Okay, get the summation of each component square, root of each component square. So the answer of norm u equal to 3 third, equal to 3 third 7. Okay, for the distance, we take the difference between u and v, get the component 0 or 1 or u different between u and v. So 1 minus 0 square plus 3 minus 7 square plus minus 2 square and so on. So the distance between u and v is given by 58. Okay, next is orthogonality. Okay, two vectors u and v in space n are called orthogonal if the dot product or the inner product of u and v is 0. So we say that the two vectors are orthogonal. Okay, example, in the Euclidean space, for the vectors given u and v, like this component, they are orthogonal since u dot v is 0. So if we were to check whether the two given vectors are orthogonal, so we check whether u dot v or inner product of u and v is 0 or not 0. If they are 0, then the two vectors are said to be orthogonal to each other. Okay, example here, u dot v is 0. So u and v are orthogonal. Okay, for vectors in column matrix notation, we have the following formula for the Euclidean inner product or the dot product. Okay, for u and v given in the column form. Okay, so u dot product v is equal, we take v first, vector v transpose u. Okay, so this is equal, this is the same. Okay, if u and v is given in the column form. Okay, for example, u given by this vector and v is given by this vector. Then u dot v equal v transpose u. So if we transpose v first, we transpose v in the row form given like this one, and dot with u in the column form. Then only we can multiply. Okay, use the product operations. Okay, if we put both in the column form, so we cannot proceed the product operation. So using the matrix operations, so the answer is 18. Okay, answer is 18. We have only single value. Okay, if A is n times n matrix, then it follows from formula this. It follows from formula this. If A is in matrix form and properties of the transpose, then okay, let's say we have A is a matrix form, u and v is a vector form. So A u dot product v is equal using this one. Okay, the second vector we transpose and multiply with the first vector. Okay, so second vector here transpose and then multiply with the first vector here. Okay, so then we use the properties. So this is equal, do the operation for the first two vector first and then followed by operation on the last vector. Okay, and this one is the same as these properties. Okay, remember the transpose properties is the same one. It is the same one. Okay, so if we use the transpose to each vector, we get this one. Okay, so therefore using back this one, this is the same as this. So this is the first vector, which is the first one, u dot with the first vector here. Okay, so this one we get from the star formula here. Referring back to this, then we get this one. Okay, referring to this, then only we get this one. Okay, same also goes for this inner product. Okay, using the star formula here. This one put first, transpose, and then followed by first vector. This one put first, transpose, and then followed by first vector here. Okay. Okay, and then using the properties of transposition, V transpose, A transpose, multiply by U. And then this one we can distribute the vector by putting the first vector outside and then followed by the combination of the last two vector here. Okay, and then again this one use the star formula. Okay, using the star formula here. So this is the same as, okay, so this is the same as A transpose U, second vector, and then dot product with the first vector from here going back this way. From here going back this way. So we have this one. Okay, so we have this one. So having this one, the resulting formula, we get the equation of the two inner product, which is AU dot V, where A is the matrix, U and V is the vectors, equal U dot A transpose V, and second one, U dot AV equal A transpose U dot V. Okay, example verifying that AU dot V equal U dot A transpose V. Given A is a matrix form, U and V is a column vector. Okay, then so we find the left equation AU, and then compare with the right equation whether both get the same value on the left and also on the right. Okay, try to complete this and show that try to verify that the left value is equal the right side value. Okay, have given A, U, V of these vectors and matrix, try to verify this. Okay, so we have the okay, from this one, AU, and A transpose V is this one. So we obtain the left side value is 11 and the right side value is also 11. Thus, we conclude the equation on the left side given by AU dot V is equal equation on the right side, which is U dot A transpose. Okay, let's do this exercise on your own. and check whether you get the answer provided here.